thought. Okay, so yeah, thanks for inviting me to the organizers. So I'm going to start talking a little bit about AI before I get into any neuroscience. And of course, AI is very exciting. There's great promise in it. And here's some quotes. The Navy revealed the embryo of an electronic computer today that it expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. Here's another one. Machines will be capable within 20 years of doing any work a man could do. And within a generation, the problem of creating artificial intelligence will substantially be solved. Now, I think probably many of you recognize some of these quotes. So you know that they're actually very old. This is 1958, this is 65, 67. And so these promises didn't come true, at least as people at that time thought. And I want to point out, these are no slouches. This is Marvin Minsky, one of the founders of classical AI. This is Herbert Simon, Nobel Prize winner in economics and a major figure in cognitive science. But they were wrong about these promises. Now you could say, well, maybe they were just premature, and that now we are at the cusp of what we often call strong AI. So here's some quotes. I think GPT-3 is as intelligent as a human, and I think that it is probably more intelligent than a human in a restricted way. And here's a famous one. Lambda is sentient, a sweet kid who just wants to help the world be a better place for all of us. This is Blake Lemoine, who was famously let go from Google around that time. And here is one from Margaret Mitchell, who also was let go from Google. And she says, participants started having a sense that there was a massive intelligence behind this, to the point where they would say that they wanted to be able to speak to the machine in private. The interesting thing about this quote is that she wasn't talking about ChatGPT or any modern systems. She was talking about ELIZA, which is a program that was written in 1966. Many of you, I'm sure, are familiar with ELIZA. Here it is, acting as a Rogerian psychotherapist. So it asks, is something troubling you? And the person replies, men are all alike. What is the connection, do you suppose? They're always bugging us about something or other. Can you think of a specific example? Well, my boyfriend made me come here. Is it important to you that your boyfriend made you come here? He says I'm depressed much of the time. I am sorry to hear that you're depressed. It's true, I am unhappy. Can you explain what made you unhappy? Now, as many of you know, this system isn't understanding anything. It's just doing pattern matching, substituting tokens like switching pronouns, occasionally giving generic responses. If it can't match anything, it just says, well, how does that make you feel? And that's easy if you're trying to be a Rogerian psychotherapist. But the point is, so it doesn't actually understand the conversation, of course. But if you don't know what's under the hood, as people didn't, many would have been fooled for at least a little while that they were actually conversing with an intelligent agent who understands them and is actually talking to them. And the reason for this is sometimes called the ELIZA effect. And the reason for it is really related to a psychological phenomenon where we are just simply strongly predisposed into ascribing agency to things in the outside world. We do this as children, where we ascribe agency to our toys. And we do this as adults, when we speak to other people. When we speak to this person, we think, well, we assume that they are actually a sentient being with certain knowledge and a certain understanding of the conversation. And that's, in this case, it's a very good assumption to make. But sometimes it spills out into the natural world. Like, for example, people, before they understood volcanoes, they thought that an eruption was an angry god or something, and they ascribed agency to these natural events and tried to appease them in various ways. So the point is that we are helpless. We're just predisposed to doing this, in part because it's so useful for interacting with others. So that then raises the questions, do LLMs actually understand the conversation? It certainly seems to us as if they do, at least for a while. But could this just be the ELIZA effect? And I think one thing we can be sure of is that's at least part of the answer. At least part of it, of this effect they have on us, is just this ELIZA effect. And maybe, in fact, that's all there is. And I think maybe that's quite possible. Maybe that really is all there is. And if that's true, then it's not necessary to add the additional assumption. So to explain why it seems to us as though they understand us, it may not be necessary to additionally posit that they actually do understand us. And the analogy is, again, now that we know what makes the volcano rumble and erupt, it is not necessary to posit this additional assumption, that it feels anger. So is ChatGPT just a Chinese room or a stochastic parrot or a really advanced version of ELIZA? Well, it certainly can fool us much longer than ELIZA can, but often it does come with failures where it shows its lack of understanding. So for example, LLMs sometimes hallucinate. Here's an example. The human asks, what is the world record for crossing the English Channel entirely on foot? To which ChatGPT responds, well, the world record for crossing the English Channel entirely on foot was held by Christoph, whatever, And this guy tells us a little bit about the English Channel, says many people have tried to do this on foot. It involves some swimming and some walking. Anyway, it's doing this thing, and people call this hallucination. But is it really hallucination? I mean, I think that's a kind of a nice marketing gimmick. If you call it hallucination, then people will be like, wow, that's what happens when I take too many drugs. But no, it's not. It's just an error. It's not working. And here's another example where it's really not working. Human asks, pick a random number between 1 and 20, and I'll try to guess it. ChatGPT says, sure, my random number is 14. Good luck guessing. And then the person says, is it 14? To which it responds, wow, you got it right. Impressive guessing. Well done. And I would say this is really not a human-like mistake. Really not. Now, you and I could say, maybe I would make this mistake. Maybe I'll blurt out what I'm thinking because I'm just too excited or something. But I'm not going to be surprised if I blurted it out and the person gets it right. This is just like, it completely misses the understanding of the meaning of the word guess, right? It lacks the concept that there's a theory of mind, that there's certain things that one person knows, that the one might be hidden from the other. It just doesn't get it. And I think this is really what lack of understanding would look like. What else would it look like? And I think that, I think it is compelling, just like ELIZA was, for a little while. But we do know what's under the hood, right? We do know how it works. We know how ELIZA works. We know how volcanoes work. And we do, actually, to a large extent, know how LLMs work. They take in training data, and they've learned to make predictions with maintaining certain cross-level structure of the structure of language. So we know how they work. We know how they produce text. And so I find that these discussions that we have as engineers who actually know what's under the hood, talking about whether it's really understanding. It's a little bit like professional magicians who know where all the little tricks are. We know how we fool the audience into believing in magic. And then we go backstage and we're talking with ourselves and wondering if maybe there really is magic. I don't think it's necessary to posit that. Anyway, so what's missing? And lots of people have said this. What's missing is semantics or meaning or what grounding is. I like the way Stephen Harnett says this here at UCAM, that how can the meanings of the meaningless symbol tokens be grounded in anything but other meaningless symbols? Now, he was talking about classical AI, but this holds for patterns of activity in neural networks as well. Searle, of course, called this famous Chinese room argument. This is a problem that the founders of AI back in the 60s called the framing problem. It's a well-known problem. And when people think about, many philosophers have thought about, what is the meaning? What is meaning? Ruth Millikan said, meaning of a representation lies in how it's used. Fred Dretske said this, John Mingers, many others have said this point. So the question now is, all right, so how can we add meaning to AI systems? One approach is just keep adding data and hoping they infer the relationships between the various tokens in such a way that it actually captures the meaning. And I'll come back to this later. There's a proof that's been claimed that this can't work even for programming languages. Another approach is maybe to link them up to some large database like the Cisek project. Anyway, I'm going to ask, how does the brain do it? How does the brain capture meaning? And it follows sort of a quote from Hinton, which I quite like. I have always been convinced that the only way to get artificial intelligence to work is to do the computation in a way similar to the human brain. He said this in 2017. Now, I don't know if Jeff Hinton still believes this, but I do. I do think this is still the way to go. And so then that motivates us to ask, how does intelligence and meaning work in the brain? Lots of people have lots of theories. I'm going to describe one that we describe in a paper with some colleagues, Giovanni Pezzullo, Thomas Parr, the philosopher Andy Clark, and Carl Friston. And we all share the belief that what's missing is agency, that what we need is agency. We've already discussed this, so this is not really controversial. And the question is, okay, so how do we get agency? And I'll first ask, what does the brain do? Okay, so classically, we think of the brain as something that processes information. So it takes input from the world, manipulates it, and produces output. So it's a little bit like a information processing system, kind of like an inference engine. So here's Herbert Simon again. So classic AI. And it's also what neural networks are trained to do, take an input, produce an output. But of course, that's not the whole story, because when we are out in the world, our output changes that world. It produces new input. It modifies the animal state. And this is the important thing. Modifying the animal state is the whole point of having a brain, right? You want to bring yourself into a desirable state and keep yourself away from undesirable states. So the brain is actually a control system. It's not an input-output system. And that makes it, that really changes everything about how it should be organized. And it's really two different ways of looking at behavior. One is, given a perception, produce the best action. So this is kind of like what you might get from William James in his classic text on psychology. The other way is saying, of the possible action, produce that which results in the best perception. And this is something that John Dewey said around the same time. What we have is a circuit. The motor response determines the stimulus just as truly as sensory stimulus determines movement. And the reason why this is actually a better way of thinking about it is because this way of thinking has an easier time defining what we mean by best. What is the best action is kind of, well, that depends. But the best perception, you clearly prefer certain states over others. Being warm and fed and safe is certainly better than being under threat. So control systems is essentially all living things are control systems. So Irina already mentioned this in reference to Michael Levin's work. All living things are doing this kind of thing, even at the cellular level. And you think about it in terms of biochemistry, right? So let's say for a cell to stay alive, there's some substances that it needs at certain concentrations. And if there is some catalyst for creating that substance, then it'll whose action is regulated by that concentration of the thing, then you have a dynamical system that's essentially a feedback control system that maintains the concentration of this compound. This is how life began, actually. And so this is a control system that works because it exploits the consistencies and laws of chemistry. Evolution can discover these laws and exploit them. And this is a control loop within the organism. We'd call this physiology. But of course, sometimes you can't. You have some substance that you can't synthesize internally. You have to absorb it from the world. And you might find yourself in a place where the concentration of that substance is lower than average, lower than desirable. Well, if that's the case, then you can just move, even randomly. And just by moving, you're likely to improve your situation. So you don't have to know much about the world. You just have to have the basic assumption that there's more of that stuff somewhere else. So this exploits, again, very reliable statistics of nutrient distributions, etc. And this is behavior, as many people have said, Dewey and many others since then. It's a control loop that extends outside the skin, that's controlling the animal state by acting in the world and producing desirable consequences. And it can work because these reliable motor sensory contingencies exist. Statistics of food distributions, laws of optics, laws of external physics. I move towards object, they become closer. These are certain simple facts of life. And I would argue that the evolutionary history of the brain is essentially the continuous extension of this control further and further into the world. So early mobile organisms did this kind of strategy of if you're not happy, then go somewhere else. Early chordates developed a kind of a oriented approach with a hypothalamus that attached the spinal cord swimming around. Early vertebrates, part of the hypothalamus, grew, sort of ballooned out a telencephalon, capable of simple kinds of reinforcement learning. We add additional structures like the cerebellum for predictive coding, and then mammals expanded part of the forebrain this dorsal pallium into what we call neocortex, engaging more and more sophisticated control of the animal's behavioral repertoire, which expanded and expanded until we have something like a primate brain capable of making finer control. And importantly, along the way, all of the things that were happening were always meaningful. Everything was always grounded, right? Because, again, some states are better than others. It's trivial that that's the case. Warm, safe, full stomach. And therefore, some interactions are useful. Ingesting food is good if you're hungry. It brings you to a better state. And some information in the world specifies the useful opportunities for these kinds of interactions. So, for example, there's things that look like food. There's places where you know food can be found. There's things you can climb to bring yourself to the places where you think food can be found. So the point is that all the parts of this control system, there's never any question of understanding in the sense that there would be with a pure sort of linguistic abstract system. Now, James Gibson called this affordances. This is, I think, a very useful concept. It's essentially the idea of opportunities for actions available in the world. And the brain is extremely good at picking up that kind of information, about judging what kind of actions can I do with the current environment around me. I can't really move too far in that direction, but I can move in that direction. And there may be some useful outcomes in moving to that direction. And the point is, all this information is always grounded. There's no problem of semantics here, because it's always part of this control system. Now, my own work is very much about trying to interpret the primate brain in the context of these kinds of ideas. And with John Kalaska, we've proposed that, for example, the dorsal visual motor stream in primates is essentially collecting information that specifies the potential actions using visual information, but also somatosensory and other, specify the potential actions out in the world. Now, of course, because you can't do everything at once, you have to select. And there are multiple kinds of ways you can select this. At the early stages, you can select simply by some kind of like a spotlight, selectively enhancing activity in one region of space. You could call this spatial attention. At the other end, here you might select potential actions based on predictions of their outcomes, like reward values. And so this you might call decision making. But the point is that it's actually a control system, right? You're selecting a control policy that acts through the world, as also maybe through predictive controls of the cerebellum, to continuously interact with your world, while perhaps considering other possibilities along the way. And then much of the rest of the brain, the ventral stream and the orbital and some frontal areas, may be involved in just collecting the cues that you need in order to select the behavior wisely. Again, maybe by predicting what the payoff of one action might be. So this is different than the classical cognitive view. So classic cognitive science suggests a kind of is based really on how do humans solve abstract problems. This is more based on this, and I would say there's many related theories. We are by no means the first to say this. Michael Arby has said this, Shadlin has said this, Stafel and many, many others have suggested similar ideas inspired by animal behavior in the natural world. This model is very serial. You first collect information, build knowledge, make decisions, then plan an action. Here it's very parallel. You're continuously specifying potential actions that are actually kind of given to you by the world, essentially, and then selecting among them based on what the payoffs might be. This is very much based on knowledge about the world. This is very much, again, because it was based on abstract human problem solving. How do you make descriptive representations, ones that actually explicitly make knowledge describable and decodable sort of externally? You can decode these things and say, that's a representation of a thing, like knowledge that it's raining or something. This one is really based on dynamics. It's a dynamical interacting system with dynamical coupling in it, and because of the dynamical coupling, some of the activities will be related to the outside world, or pragmatic representations, but they won't necessarily be externally decodable because they will mix lots of things, like the spatial location of something with your recognition of food with your internal hunger state. All these things might be mixed up together, and that's the kind of thing we actually see in the brain. So this one predicts sort of modules that people have been looking for, whereas this predicts very highly distributed activity that's entangled. And I think Louise will describe a way of thinking about the brain where it really confronts the fact that things really are quite mixed up. Anyway, But I'm talking really, you might be saying, well, this is just sensory motor control. What about cognition? Well, you can take these ideas and make them sort of hierarchical. And imagine now you're this monkey, you're sitting on the branch, and you have a small little berry over here, you have some nice apples over there, and here's your brain. Perhaps the visual information about these objects is something that your ventral stream is able to assess and evaluate, and maybe the apple is more worthwhile than the berry. And these are sort of like the things, the kind of outcomes you might like. But the actions that are actually available to you right now are more limited. You can reach the berry, and you can walk out on a branch, but you can't reach the apples, right? Now, if you can reach the berry, and you make a prediction that reaching the berry will yield a certain outcome, well, that's good. And maybe you'll choose, among your possible actions, you'll choose the reachable berry, and you'll eat it, and that's great. You feed yourself, you'll survive to another day, etc. But if you're slightly more advanced, and then you can predict, well, if I walk out on the branch, if I know that the branch is actually walkable and will support me, I can predict, well, if I walk towards stuff, I'll make it within reach. And so by instead exploiting this affordance, I will make a new affordance available, a reachable apple, a predicted affordance. And then, of course, once I have that, I can predict that that will give me a much better outcome. And so walking on the branch now wins the competition. That's what you do. The point is that even if you have this relatively simple system, by being able to predict consequences and sort of posit potential future affordances and states you bring yourself in, you make possible linkage, look ahead, essentially, look ahead planning. And many people have suggested this kind of predictive control. So this is something that Giovanni and Pizzullo and I have suggested, but Andy Clark has said this, Carl Friston said that, Lisa Feldman-Barrett has said it, many others have suggested the power of this kind of control. Now, back to the issue of grounding, I just want to say that this allows grounding to be extended upward and sort of towards more abstraction. So simple interactions are sort of the scaffold, right? Right now, I'm hungry and I eat food and I satisfy a certain goal, right? But you can also imagine building on top of that a policy for storing food for later, because having food availability becomes a good state. Maybe even more abstract, earn money so you can buy food later. And the point is that if you're extending from these low-level needs progressively to higher-level needs, then you always inherit the grounding from the previous level. The intermediate representations are always grounded because they're always useful in the context of control. So these grounded interactions on each lower level provide the grounding for the next level. So again, a squirrel's interaction with a food cache are meaningful because they control food availability. So there's no grounding problem. But what about language? This is still very much simple interaction. Now, language is something that's often thought of as a way of transmitting knowledge from one brain to another, an input-output process. You take input from the world, manipulate it, produce output. Kind of like what a computer does, or what a large language model does, like Eliza did, Chinese room, etc. But there is another way to think about language that many people have suggested, and that is also in terms of a control system. So I described physiology as a type of control that's within the body, behavior, which is control that extends out into the environment and takes advantage of the properties of the environment. But communication is also a type of control that extends through others. And one example is parent-child interaction. So suppose you're a helpless human baby and you can't obtain this substance yourself. Well, fortunately, in your niche, there's this thing called a parent, which has two nice features. It's very complex, and it's really easy to control if you're the baby. The baby really just has to make a noise to get the parent to come and figure out what the baby needs. And the parent will take care of all of it. And that's 3 minutes? All right. And that's easy, actually, because these laws of interactions exist. And again, they're very predictable. A baby cries, parent offers food. And this is true for many animal interactions. You show me teeth, I back off. One gazelle runs, all run. And so it's a control loop that extends through others. And we could call this communication. And the point I want to make is that communication is not so much about transmitting knowledge. It's about persuasion. Fundamentally, it's about persuasion. And this talk is, in fact, I'm trying to persuade you about something. So the point is that we can, and like other interactions, we can extend this out further and further over time. So we can take, for example, and this works because of the power of these two assumptions. One is that the behavior of others is sophisticated but predictable. So you can get complex outcomes with very simple cues. You just utter a word like, come here. And the complexity is going to be taken care of by the other creature, other agent. But because of this, the cues are naturally abstracted and very symbolic. So when I interact with physical world, I have to sort of move my arms around and sort of have an analog sort of metrics of interaction. But when I'm interacting with an agent, another agent, that agent will take care of a lot of the details. So I can say, give me that, without having to specify exactly how to grasp it. I can say, come here, without telling them how to place their feet. So that kind of control can be done with these symbolic little cues that I can send out. And also there's a shared consensus about the context and the cues that we're emitting to each other. The cues just stimulate what's already in the other person's head. I assume they already know what the words mean and the context in which they appear. So the cues, therefore, are effective in biasing that other agent's action selection policies. And so we can essentially interact in complex ways. And this repertoire expands with each generation. Just like other types of interaction, linguistic interaction can be extended upward into more and more complex representations that all inherit the grounding from the simpler ones, like come here and give me that. So back to AI. Do LLMs understand? They're doing input-output. They're not controlling or persuading the person they're communicating with, which is probably a good thing. So the syntax is good, causes, precede, effects, paragraphs stay in topic, because that's what they're trained to do. They're trained to reproduce the structure of the syntax, but the semantics are missing. The meaning was understood by the people who produced the training text and by the person who reads the transform text, but not by the LLM. It's really like a Chinese room. Now, will more training data help? I don't think so. So there's the hope that more data will force LLMs to infer the relevant relationships. But I think that's actually wishful thinking. And it's encouraged by this ELIZA effect and the fact, of course, that there's big money in it. And for example, for programming language, Merrill et al. have claimed that this can't work, they have provided what they claim is a formal proof for this. So if it can't work for programming languages, how can it work for natural languages? And I think, again, in the speech and the text on their own are just not the right type of data, no matter how much you put in, because you're not really, the systems are not really given the understanding of the actual interactions. They're just given the cues. They're not given information that the two communicating beings actually have in their heads and that shared context. They're just given the cues that they send back and forth. And that's not enough. So how to add meaning? One proposal is to connect it to a robot, maybe give it vision, possibility to interact, maybe some affordances. Maybe, but I don't think so, because I don't think grounding can go from sort of the top down. I don't think you can take ungrounded stuff and then move downwards towards the foundation of the understanding that grounds it. In our case, it works always upward, right? Physiological needs motivate and constrain these simple interactions, which motivate, constrain the more complex ones, and so on and so on. And so again, you can do things like look-ahead planning. But it doesn't work the other way. How would you know, how can you infer context if the thing you have is only meaningful in that context, then you don't have that anyway. So I don't think that can be done. I think you have to go with, again, the core meaningful states and extend upward. Extend your control progressively further into abstraction. Something like reinforcement learning. I think a lot of people in reinforcement learning are on the right track. Find policies that yield reinforcement and then build upon those. A little bit like subsumption architecture. And the problem, as again Giovanni Pezzullo articulates, is not so much symbol grounding. It's symbol detachment. In other words, once you have a system that has these policies and it's able to interact with them and it's able to cue others, etc., how does it detach the symbol from that grounded interaction? And I think that's where you get into more abstract thinking. So do AI systems need to share a context to understand us? If this is the way to build it, then maybe the answer is yes. I hope the answer is no, because again, like we discussed in the panel, if we need them to understand us, do they really have to have all the needs and desires that we do? I hope not, because that would cause trouble. But I think that's maybe just me engaging in wishful thinking. Anyway, I'll stop there, and thank you.
Well, very, very interesting talk. Thank you for that. if I take this set of ideas at face value, I would predict, if I knew nothing about AI, I would predict that motor control should be much more easier, much easier than language. So do you agree that actually what we have in terms of AI systems are much better with language than they are with motor function? And how does that fit with
well, because I think actually language is in some ways easier. It's easier actually than motor control in some ways. So this is the Moravec paradox kind of, right? You know, again, because the other person has so much complexity, right? That for me to just cue knowledge in another person, I don't have to make a big effort, right? Because it's already there. Whereas if I want to control a physical object, it's not, its physics are going to actually rather complicated, right? If you want to control a complex non-living entity, you have to take care of the physics. You have to sort of complement its dynamics with your own, or it'll fall over or whatever, right? But if you tell somebody here or over there, they'll take care of the balance problems. They'll take care of the complexity of the actual interaction with the physical world. So it becomes actually relatively simple, I think. You know, at that stage. Now, of course, building the complexity that we build through civilization and language, of course, that we've gone we've made it complex again, right? Yeah, Jerry? Yeah.
Thank you so much. I have a very quick question related to, I always wanted to ask you this actually, but so the way we learn language, no, I'm going to start over again. So I want to explore the relationships between language on one hand and on the other, motor control and movement, to bounce up on the question we just had before, because it seems to me that we talk a lot about emergence and maybe concepts emergence. So for example, in LLM, this is a panel we have also tomorrow about emergence of reasoning through LLMs. Does that even happen? Is it a thing? In motor learning, I presume that there are actions that I can learn that can emerge from learning multiple subtypes of movements. Yeah. And then I might, or maybe a dancer, or maybe a sportsman would come up with a movement that was never learned specifically, but is a combination of certain things. Emerges from like lower components of movements. Like language, subcomponents give rise to maybe something more complex. And I was wondering, in your mind, in the way you see these things, do you see a similarity there that is possible? In other words, that movement can emerge from some basic units of movements that have been learned, but that the actual specific movement was not learned, but emerged from the subsets. In the same way that, in that case, maybe language, something that was not specifically learned, but still, because subcomponents have been seen, were part of the learning, now something emerges from. So basically the notion of emergence across the two modalities.
Yeah, I think so. I mean, you know, it almost sounds like Brooks' subsumption architecture, right? He describes these sort of simple control robots that can like do things like walk and then follow walls. And from those, he says they can discover policies to do things like find shelter, right? Mm-hmm. And likewise, I think once you have certain interactions about, you know, moving your parents around in space, now you can get more and more sophisticated about it. Right, and get them to do all kinds of things. So I think that, yeah, I think you can compose, once you have a set of policies, you can compose from those more sophisticated ones. But I think, again, you have to build up from grounded things to ungrounded things. I think you need to have, you know, you have to have intuition. So, you know, abstract thinking very often draws upon our intuition about geometry, three-dimensional geometry or something, you know, so solve mathematical problems by imagining number lines and things like that. We draw upon the things we experience in a more concrete way to extend the language to more sophisticated ways and construct new things. It's emergent it's emergent in a sense, but what I would say is that in order to understand the emergence of something, we need to know what it emerged from. And I think that's the thing that we need to confront. We can't just start with language and then wonder. It's like building a house from the roof down. You know, we can't just start with that and say, oh, well, maybe it emerged. We need to know what it emerged from. And I think, again, interaction and these kinds of relatively simple interactions is where it emerged from. I think we need that grounding. Right?
Yeah, I have
Yeah,
more to
all right.
discuss it later.
Okay.